great. Thank you.
Okay. Great. Okay. Eva Dundas entered the doctoral program at Carnegie Mellon in August 2010. Prior to that, she had completed a master's degree at Harvard University under the mentorship of Chuck Nelson, and she was trained as an undergraduate student at the University of Pittsburgh, where she conducted research both in the lab of Mark Strauss and also had an independent research advisor who was Mark Johnson at Birkbeck College, London. So she has had an illustrious trajectory. During the course of her training, she has published 7 manuscripts. There actually are a few others in the hopper as well. 5 of these 7 manuscripts, she serves as first author on 5 of these 7 manuscripts. She has a long series of presentations and posters that she has presented at various conferences and meetings. She has received a number of awards during her tenure, including she was a trainee on the B Squared Research Fellowship. She received R.K. Mellon funding. She received a travel and mentorship grant to attend the International Psychological Meeting,
Congress of
Psychology, and even I met in Cape Town during the course of that conference. She has been a sterling member of the psychology department, has been citizenly in many ways, helpful in many ways, and her contribution has been really valuable at that level as well. So I now invite Eva to give us her presentation, and we take this out the way so that you have a bit more room.
All right, thank you, Marlene, and thank you everybody for coming. Today I'm going to be talking to you about the development of hemispheric specialization for visual, word, and face processing. To start this off, the adult human brain shows selective activation patterns for different cognitive functions. One of the most widely researched is language, which shows selective activation in this left frontal region here. We also see selectivity for visual information in the back of the brain over here. We also see other cognitive domains like sensory motor functions and different higher level visual processing selectivity, which I'll be talking about today. So in addition to showing selectivity in different regions of the brain, you also see selectivity on one side of the brain or the other. Most notably, we see that language processing is more selective in the left hemisphere than in the right hemisphere. So there are different arguments for what brings about this selectivity. One is that the brain is hardwired this way, so it's predetermined that these different processing regions are going to be in a specific location versus another. Another argument is that the brain has intrinsic processing properties that make it better suited, or make different regions better suited for processing different cognitive functions. So the third argument, which I'll be exploring today in my dissertation, is that these regions of selectivity develop through interactions between different cognitive systems and develop out of experience. So the idea behind this principle is that the brain has limited space. Not all regions of the brain or all neurons can be connected with all other neurons in the brain. So in order to efficiently accommodate all cognitive functions, there needs to be some organization of selectivity to accommodate all of these functions. So the idea is that interactions between these cognitive domains develop this final state of selectivity that you see. And the current dissertation is going to explore this interactive development between cognitive processing within the realm of visual, word, and face processing. So to give you an outline of my talk, first I'll go over why words and faces are a good domain to explore this interactive development. I'm going to propose a theory for the relationship of their development. show some evidence that already exists that these two domains really are not emerging independently of each other. And then I will present 5 experiments that explore this relationship. Okay, so why words and faces are a good domain to explore this interactive development. One is that they're processed in a very similar region of the brain. It's the inferior temporal cortex, which is on the underside of the brain here. And in addition to be processing in a similar place, words show a bias to be processed in the left hemisphere over the right, and conversely, faces show a bias to be processed in the right hemisphere over the left. So we can look at how this relationship is unfolding and how this lateralization to the two hemispheres is emerging to understand this interactive development. Okay. Secondly, we can study the lateralization with ERPs. ERPs are easy. You can run them on yourself. So this is just an EEG cap. So it's a cap of sensors that you put on over a head, and it records the electrical output that's given off at the scalp. So this is a layout of all the electrodes. And with words and faces, and these back posterior electrodes here on either in the left and the right hemisphere, you can see a distinct neural signature of processing words and faces. So what you do is you take this continuous EEG signal that you get when you're presenting words and faces, and you slice up that signal. And if you time lock the signal to when you present a word or when you present a face, you see this distinct pattern here where you see a negative deflection of the voltage around 170 milliseconds after a face is presented, and it's stronger in the right hemisphere than in the left, which is consistent with seeing greater fMRI bulb activation in the right hemisphere than in the left. And conversely, you also see the same neural signature with words. You see a negative deflection of voltage around 170 milliseconds after you present a word. And it's stronger or more negative in the left hemisphere than it is in the right. Okay, so I'm going to come back to this because I use this in most of the studies I'm going to present today. All right, so to go over the theory of how words and faces might be developing neural selectivity dependently on each other, starts with the idea that both words and faces really want to be processed in this middle fusiform region. They both require high visual acuity to discriminate between them, because the changes in between words and the changes in between faces are very, very small. So this region of cortex is really good at processing that type of visual information. Second, words also require language information. So to efficiently read, words need to be connected to language regions, which, like I said earlier, are mostly in the left hemisphere or predominantly in the left over the right. So words want to be in the left visual cortex or inferior temporal cortex to be close to frontal language regions. And as a result, because words take up the space, faces then become instantiated in the right hemisphere to avoid competing with words because they do have conflicting visual information. Okay, just to illustrate this, I have a little illustration. So the idea is before individuals know how to read, they're getting the visual information from words and faces, and they both go to both hemispheres. When individuals are learning how to read, they're connecting this left language region with words, so words become more strongly processed in the left hemisphere, and because words are not taking up the space anymore, then faces want to shift over to the right hemisphere. So you see this trade-off. Okay, so there's evidence that words and faces really are taking up the same cortical space. There's one study that shows a subset of voxels in this inferior temporal cortex are actually selective for both words and faces. You also see that patients that have left inferior temporal cortex damage who demonstrate a difficulty in reading, when you really press their face processing ability, they also show a deficit. The same is true for individuals with a right inferior temporal cortex damage who show face processing deficits, also show graded word processing deficits. So evidence for this actually being a competitive relationship, when individuals are not taught how to read until later in adulthood, you see a reduction in this left fusiform activation to faces as a product of how much reading experience they have. And you also see a corresponding increase in the right fusiform activation to faces as a product of how much reading experience they have. And you also see this in young children as they're learning how to read. You see a reduction in the left fusiform region to faces as a product of letter knowledge. Okay, so for the dissertation, I'm going to first explore the developmental pattern of how words and faces are developing selectivity. The idea is that understanding this development or tracking it systematically in individual children will tell us if these two are really independent of each other or not. Second, I'm going to look at what happens in the adult brain when there's a disruption in the typical lateralization profile for language. So if faces are really dependent on word lateralization, if adults show a disruption in the typical language and word profile, we should also see a disruption in face lateralization. Third, I'm going to investigate the behavioral consequences for processing words and faces based on having a lateralized system. So I'm going to compare what happens when you process words and faces simultaneously in individuals that are more lateralized for words and faces versus less. Okay, so objective 1 is to go over the developmental profile. Again, the motivation is to understand this pattern in individual children will tell us about their relationship. So the prediction would actually be that words become lateralized before faces, despite children being exposed to faces much earlier than they are to words, and that we could actually see this relationship between the degree of lateralization for faces and words over development. So for the first experiment, I have a behavioral experiment with a group of adults, young adolescents who are 11 to 13, and then children who are 7 to 9 years of age. All were right-handed and native English speakers, monolingual English speakers. So the behavioral paradigm I used is a same, different matching task. Participants see a fixation, followed by a centrally presented stimulus, and then it disappears and you see a stimulus in either the right or the left visual field. The idea is that information in the right visual field is predominantly going to the left hemisphere, and information in the left visual field is predominantly going to the right hemisphere. So the second stimulus is presented briefly, so participants really aren't able to, and it's random, so they're not able to predict which field it's going to, and they're not able to make a fixation to it. So we really are assuming that most of that information is going to one hemisphere versus the other. So stimuli are either face pairs or word pairs. Face pairs are within gender, presented in grayscale with hair cues removed. So it actually is quite difficult even for adults. And the words are all 4-letter words that changed by one of the internal 2 letters. So what they're saying is if the second stimulus is the same as the first one or if it's different. So it's the same, different judgment. So what that allows us to do is to look at accuracy for making the same, different judgment for faces in one visual field versus the other, or one hemisphere versus the other, and look at accuracy for discriminating words in one hemisphere versus the other. Okay, so what we see with adults is the typical profile where when they are discriminating words, they're more accurate when the words are presented in the left hemisphere. This corresponds with seeing greater selective activation in the left hemisphere than the right for words. That's right here. And then we also see greater accuracy for words when they're sent to the right hemisphere than to the left hemisphere. And this is the standard profile that has been seen many, many times. When we look at the young adolescents, they show the same profile for words with greater accuracy in the left hemisphere than the right hemisphere, and the accuracy level is equivalent to adults at this age. With faces, however, they show no difference in hemispheres for processing faces, despite being at the same level of accuracy as the adults. So second, for the young children, surprisingly, they actually show the same hemispheric advantage for processing words. So the left hemisphere is more accurate than the right hemisphere for processing words, even at the 7 to 9-year-old age, though the accuracy is less than the adults and adolescents. And for faces, again, we don't see any hemispheric advantage for processing faces, and the accuracy, again, is lower than adults and adolescents. So we were interested in looking at what's driving this face lateralization. So we took an index of lateralization by taking accuracy in the right hemisphere and subtracting accuracy in the left hemisphere. And what we found is that reading comprehension scores taken on a standardized test actually predict the degree or are related to the degree of lateralization for faces. And so we don't actually see, or that this is also taking into account accuracy and age. So it doesn't look like it's just a maturational effect or related to performance on faces, that it's really this relationship to reading that is related to this lateralization for faces. Okay, so in experiment 2, we wanted to replicate this and also take an EEG recording while they did this, so we could look at that N170 I discussed earlier with ERPs. So what we did is we had the same behavioral paradigm, and we had them do this in the EEG booth while the recording was being done. And then we were able to take ERPs, time locking to the centrally presented stimulus, and then take the clusters of left hemisphere electrodes and right hemisphere electrodes to look at that N170 lateralization. Okay, so the behavior results replicated experiment 1. Adults show this pattern where they're more accurate for words in the left hemisphere than in the right, and more accurate for faces in the right hemisphere than the left. Children showed the hemispheric advantage for words, and again did not show the hemispheric advantage for faces. So these children were actually, we collapsed across the age group. We had 7 to 11-year-olds in this group. So when you look at the ERP signal, again, this is the N170, this negative deflection after words and faces are presented. Adults showed the standard finding, which replicated the behavioral data, but the N170 was more negative in the left hemisphere than in the right, and more negative for faces in the right hemisphere than in the left. Children replicated their behavioral data with a more negative N170 for words in the left hemisphere than in the right, and no difference in N170 amplitude for faces across the 2 hemispheres. So again, we were interested in what was predicting this lateralization for faces. And what we found is that there was actually a relationship between the N170 amplitude for faces in the right hemisphere and the N170 amplitude for words in the left hemisphere. So the more negative the amplitude for words in the left hemisphere, the more negative the amplitude for faces was in the right hemisphere. So we do see this trade-off relationship. Okay. So to review the developmental profile, word lateralization is occurring before face lateralization. And we see this relationship between the degree of face lateralization and reading comprehension scores, and also in the amplitudes of the N170 for words and faces in the left and right hemispheres. So these data do support the model presented that words and faces aren't developing independently of each other. Okay, so for the second group of experiments, I'm going to explore the pattern of lateralization in adults when there's a disruption or a deviation from the typical lateralization profile. The idea behind this is that if words and faces really are not independent of each other, we would see disruptions in typical word and face lateralization, even in adulthood, if there is a disruption somewhere along the stream of lateralization. So for the first experiment, to remind you of the typical profile that we see in adults, what we're arguing is that this left lateralized language pressure is what's driving words to become lateralized in the left hemisphere and then pushing faces into the right hemisphere. Well, what happens if language is more distributed and there's not this strong left pressure for words to become lateralized? What happens to face lateralization? So to do this, first we look at left-handers who as a group have more distributed language processing. So we actually see that the degree of right hemisphere lateralization or left hemisphere lateralization for language is related to the degree of right-handedness. So by introducing a sample of left-handers, we're creating more variability in the language distribution. So we have a group of right-handers and a group of left-handers, and we assessed handedness by using the Edinburgh Handedness Inventory, which is a questionnaire of hand preference for different activities, which gives us an idea of how strongly handed individuals are. So again, we used the same hemi-field experiment while collecting ERPs. And for the behavioral data in right-handers, again, we replicated the same behavioral finding with greater accuracy in the left hemisphere than in the right hemisphere for words, and greater accuracy in the right hemisphere than in the left hemisphere for faces. Left-handers showed the same hemispheric advantage for words with greater accuracy in the left hemisphere, but no difference in accuracy across the two hemispheres for faces. And again, the ERP data replicate the same finding with a greater N170 amplitude for words in the left hemisphere than in the right, and a greater N170 amplitude in the right hemisphere than in the left for faces. And in left-handers, we see a more negative N170 in the left hemisphere than in the right, and no difference in N170 amplitude across the two hemispheres. So one, this was a little surprising because although we do not see face lateralization in left-handers, they are actually lateralized for words. So we were interested in what's driving the degree of lateralization. So we took this index again, subtracting the left hemisphere N170 from the right and N170 for faces. And what we found is that the amplitude of the N170 for words in the left hemisphere is actually driving this lateralization, or related to this lateralization for faces. And this is above scores of handedness and also accuracy for faces. So while we were looking to introduce left-handers into the sample to create variability in language distribution, we see this relationship between handedness, but above that, it's the amplitude for the N170 for words in the left hemisphere. That's related to face lateralization. Okay, so ignore that arrow right now. So again, to review the typical profile, it's really the pressures from language that are driving this cascade of lateralization. If we examine individuals where there's a disruption in connecting this language region to the visual processing of words, then we would also see consequences for face lateralization. So to do this, we look at individuals with developmental dyslexia. So developmental dyslexia is thought to be a disorder where individuals have a really hard time discriminating phonemes, and this has consequences for their ability to connect phonemes with graphemes, so making this connection between the language and visual information. And we already do know that this has consequences for the lateralization of the visual processing of words. So what we're interested in looking at is if this has consequences for the lateralization of faces. So we use the same experiment again. We have 10 controls and 10 developmental dyslexics, and we also collected standardized measures of reading on these individuals as well, on both groups. So we also added a different stimulus categories to serve as a control. So we have phase scrambled images of the faces. We were doing this in order to subtract out the N170 for the phase scrambled images from the faces in order to remove the signal from more lower level visual processing. The same thing, we used symbols for words. The idea is that this is taking out, again, the lower level visual properties. We Didn't actually get a good signal with the symbols, though. One idea is that maybe they actually were readable. So if you have pronounceable letter strings, they also show left lateralization. So moving forward, we're going to just ignore the symbols, but I do subtract the contrast for faces. Okay, so looking at the behavioral data, controls, I switched to inverse efficiency here because the DD group did seem to show a speed accuracy trade-off. So we, using inverse efficiency, we see the same pattern where lower score means better performance. So better performance for words in the left hemisphere than in the right, better performance for faces in the right hemisphere than in the left. While it's trending with DDs, and it looks like it should be a significant interaction here, it's not, but there's greater variability and poor performance in the DD group. So when you look at the N170 amplitude, controls show the standard finding that I've been presenting, and DDs show a greater N170 for words in the left hemisphere than in the right, and they show no difference in N170 amplitude for faces across the two hemispheres. And the amplitude is for words is actually lower. So again, we were interested in what's driving this relationship, and like with the children and the left-handers, we see that the amplitude for faces in the right hemisphere is related to the amplitude for words in the left hemisphere. So we do see this relationship between specificity in one hemisphere, the left for words, and specificity in the right hemisphere for faces. And the same is not true when you look at the opposite hemispheres for each stimulus category. Moreover, we were interested in how this related to the standardized measures collected on reading, and we do find that it is scores of phonological awareness that are related to the degree of face lateralization. And this fits really well with the theory and the idea that the deficit in word processing is really coming from a deficit in phonological awareness in these developmental dyslexics. So while this looks awesome, this guy's actually an outlier, and you take him out and it's just trending, but there's only now 9 subjects, so it's promising, but don't put all the weight on it. All right. So when there's a disruption in the typical lateralization profile, we do actually see of language. We do see disruptions in the language profile, in the face profile. So we see this in left-handers and also in adults who have developmental dyslexia, and in both cases, we still see this relationship between the specificity for faces in the right hemisphere and the specificity for words in the left hemisphere. So third, I want to explore the behavioral processing consequences for words and faces for having separate systems. So if words and faces really are using the same neural resources, then lateralization is reducing the load on those same neural resources. So we should see a behavioral effect for when individuals are presented with processing words and faces simultaneously. That's related to how lateralized they are. So for this experiment, we had all typically developing adults who were monolingual native English speakers and also right-handed. We presented 2 stimulus categories that disappeared, and they're presented by a second stimulus of one of the 2 previous categories. And they said if this second stimulus was one of the ones that they saw on the previous screen. So the 2 stimulus categories that were first presented could either be of cars, faces, words, or glasses. Cars and glasses are serving as a control here. So we were interested in looking at accuracy of discrimination for words when they were presented with a face, versus when words were presented with a car or with glasses, versus when faces were presented with a word, versus faces being presented with cars or glasses. So what we're calling this is the dual condition, so they're being confronted with processing words and faces simultaneously, versus the control condition where they're processing a word or face with a different object category. The idea being here that if there's really is neural overlap, we should see a consequence for this dual condition. So it could either be an inhibitory effect, or a facilitation of processing, like maybe it's actually just priming this neural resource. Either way, it should be different in the dual condition than it is in the control, and ideally it should be related to the degree of lateralization. Okay, so what we see, so with looking at all 40 subjects, we do see a facilitation effect when faces are presented with words over when faces are presented with cars and glasses. Accuracy for cars and glasses was equivalent, so we collapsed them. We do see this facilitation, and with words, it's trending, but we don't see it, but the accuracy for words is really, really high. So what we did is we did a median split and looked at accuracy for the lower performing group, and now we do see this facilitation effect also for words. So they're better at processing words when they're paired with faces than other object categories, and the same was still true for faces. They were better at faces when paired with words than other object categories, suggesting that there really is overlap in the neural resources for processing words and faces. And if this is the case, we should see a relationship between this facilitation effect and how lateralized individuals are for processing words and faces. So we performed the hemifield task on those same individuals that gave us an idea of how lateralized individuals were. And what we found is that when you divide the group based on word lateralization, the individuals who were low lateralized for words showed more of a facilitation effect than the individuals that showed greater lateralization. So this lateralization really is separating the neural resources required when processing words and faces. And the same is true when we divide the groups based on face lateralization. You see more of a facilitation effect with low face lateralization than high face lateralization. It's mostly in the words, but again, words are mostly with faces. Words are mostly at ceiling at this point. Okay, so those are the conclusions I went over. So the general conclusions are that word and face processing regions do not develop independently, and that bilateral face processing happens when there's a disruption in connecting language regions with this left, or in the left lateralization of language and word processing. And that lateralization actually reduces the shared neural resources for processing words and faces. So all of the data that I've presented support this model that words and faces are becoming lateralized through their interactions with other neural systems and with each other. So future directions. What are the initial constraints on the system? So obviously visual information is going to visual regions, and it's projecting up to have words and faces be processed in the same region. And also language is lateralized, which is putting a constraint on the system. But where's that coming from? And what are the behavioral processing consequences within normal variability of lateralization? You know, individuals are lateralized to different degrees, but within a typical individual, what are the consequences of that variation? And also, what's happening at the molecular level? So what's actually driving this connectivity and lateralization to avoid processing competition? Okay, so general conclusions. While this dissertation was focusing on words and faces, they support the idea that cognitive systems more generally are developing not independently of each other. So these aren't special, separate individual regions, but this mature pattern that you see could arise through interactions with other cognitive systems and with experience to create a more optimized processing system. All right, and so thank you. Oh no. So Marlene, my advisor. Oh no. Who has shared her brain. Oh no, keep going. This really doesn't want me to show this picture. I know, Marlene. She has shared her brain with me in more ways than one. Who's always willing to help out in any way possible, and so thank you so much for this work and everything. My committee, Dave Plaut and Mike Tarr, who've also helped significantly in this research in my graduate career. For this research developmental dyslexic study, Yafit Gabay helped with the standardized assessments on the dyslexics. Research assistants who helped collect the data. One is here, Lauren Lorenzi, thank you. She's also my roommate. An unofficial therapist. And VisCog Group's Perceptual Expertise Network, who maybe some of you are listening. SciGrads for all your help throughout this process. Lucy Erickson, who is my special cohort friend. Lori Hull and Julie Fees, and Lynn Reeder. I've been on their training grants, so thank you for the work you have done for that. David Rackison, Eric Thiessen, Ken Katofsky, and Mark Strauss, who have all helped with writing advice, teaching advice, general career advice, and all of that sort of stuff. And then family and friends. You guys are awesome. Thank you.
Okay, thank you very much, Eva, for a very good presentation. It obviously was